Hello, my name is Jacob, and in this video we're going to talk about different types of motion and go over some of the main coordinate systems that are used in dynamics. The first coordinate system is the Cartesian coordinate system, which is sometimes referred to as the global coordinate system, and it has unit vectors I, j, and k that are centered at the origin and point in the typical x, y, and z directions. This coordinate system can be modified to be centered on a body, which makes it very easy to describe the body's motion with respect to the global x, y, and z coordinate system. The unit vector for this body-centered coordinate system are ex, ey, and ez, and they're centered on the body, typically with ex pointing in the direction of motion. The global Cartesian coordinate system and the body-centered coordinate system are both very useful and can be applied to most problems, but that does not mean that they are always the easiest system to use to describe the motion of a problem. For example, if you know the path that an object takes in space, then it might be easier to use the second coordinate system, which is the path coordinate system. In this coordinate system, the unit vectors are et and en. Et is always tangent to the path, and en always perpendicular to et, or normal to the path. Et points in the direction of motion, and en points toward the center of curvature, or the direction that the path is turning. The third coordinate system we'll talk about is the polar coordinate system. This coordinate system has unit vectors er and e theta. Er points along the line that connects the origin to the body, and e theta points in the direction of an increasing angle. So now you know the main three coordinate systems that are used in dynamics. Coordinate systems are very useful, and they're used to tell you directional information about a problem. This allows you to relate any motion that's in the problem to the same axes and the same directions with the same unit vectors. So now let's apply this information to problems. Say you have a soccer ball that's 15 feet from the goal, and you know the ball is moving 3 feet per second. You want to know how long it'll take to reach the net. To answer this question accurately, you need some directional information about the ball's motion. So let's set up a Cartesian x and y axis, and we can say that the ball is heading completely in the y direction, and it's not accelerating. It's easily found that the ball will take 5 seconds to reach the goal. But what if the ball was headed 10 degrees off the y-axis in the negative x direction? It would now take 5.1 seconds to reach the goal, which is only a short time after. But if the ball was moving at a 25-degree angle off the y-axis, then it would take 5.5 seconds, which is a bigger difference. And if the ball is going at a 45-degree angle off the y-axis, then it would take 7.1 seconds to reach the goal. Technically, all these answers are correct without the initial directional information of where the ball is headed. This is why it's so important to describe a coordinate system. This way, you're able to fully describe all the motion of anything in the problem with respect to the axes. Similarly to using the Cartesian coordinate system, sometimes it's easier to use a body-centered coordinate system when the body is moving constantly in the same direction, and that direction is not completely in any of the global x, y, or z directions. Here's an example of where this might be useful. Because the object is moving in a constant direction down the ramp, we can set ex to be parallel to the ramp and ey to be perpendicular to the ramp, which makes describing the motion very easy. With a global coordinate system, you would have to write the velocity of the object like this, using the x and y components to describe the motion. But using the body-centered system, you can completely describe the motion as vex. One last important topic about the body-centered coordinate system is knowing how to do a transformation of a vector from the Cartesian system to the body-centered system, and vice versa. You can see how the body-centered system is just a rotation of the Cartesian system. And because of this, we can find the angle between them, which we'll call theta, and we can use trigonometry to find the transformations from one system to the other. Now let's talk about the path coordinate system. When you know the path the object is going to take, like this S-curve, it's helpful to describe the motion of the object with respect to the path itself. For these three path positions shown, the direction of the axes are not the same. This is because the two axes are always set up tangential to the path and normal to the path at its current position. The direction of ET is also the direction of instantaneous velocity. When describing acceleration, there is tangential acceleration along ET, which describes a change in speed, and normal acceleration, which shows a change in direction along EN. These equations can be very useful in these types of problems. They can help you find acceleration, velocity, or even radius of curvature, which is represented by P in the EN formula. This next video clip shows a roller coaster ride. You'll notice the camera angle with respect to the car does not change, even though you know the car is clearly changing direction. This is similar to how with the path coordinate system, the direction of the path changes, but the axes are always perpendicular and normal to the path. That doesn't ever change. The last coordinate system we'll talk about in this video is the polar coordinate system. This system is useful when tracking an object in the sky, or when something is moving in a circular path, or when something is rotating around a point. Here we will look at an airplane being tracked in the sky. If the radio receiver is in a fixed position on the ground, we can call that our origin. We can call the distance from the plane to the receiver r, and call the angle that r makes with the ground theta. When the plane moves to a second position in the sky, we could call it r prime and theta prime. With these equations for velocity, you can find the velocity in the ER direction or the velocity in the E theta direction. And with these equations for the acceleration, you can find the acceleration in the ER direction as well as the acceleration in the E theta direction. The last thing I'll present in this video is a simulation of two moving objects. This will hopefully make the difference between the coordinate systems clearer. The scenario plot is a good representation of the Cartesian coordinate system with the globally fixed x and y directions. The chase plot and the bird's eye plot are both good representations of path coordinate systems, where the blue body is stationary in both plots and moving through the path. The chase plot should be thought about as if you're looking along the ET direction, and the bird's eye plot should be thought about as if ET and EN were kept in the same directions and the path is moving underneath the body. Notice how the path systems mainly focus on the blue body's motion, and the Cartesian system is good for describing both bodies' motions. So, these are the three main coordinate systems that are used to describe motion in dynamics and physics problems. As a reminder, all three of these coordinate systems could be used for any problem, but choosing the right one to describe the motion in a problem makes an engineer's job much easier. Thanks for watching the video, and good luck.